Good evening, everyone. In this today's special class, we are going to talk about tree data structure. Okay, tree data structure in Python. So in Python, how to implement this tree data structure we are going to see. So tree data structure notes. You are going to get this as a separate folder, sir. For both batches, I am going to share this. Yeah. So we know already we covered two classifications of data structures are there. One is nothing but linear data structures are there, where the memory will be allocated. The memory will be allocated continuously. Okay. So memory allocation will be done in a continuous manner. Okay. So now I don't want this. So then we can go for non-linear. That means we can't give the data guarantee that every data will be available in the continuous memory location. So this memory allocation will be random. So best example for these data structures, tree and graph, right? Because if you see tree, generally how we are going to represent the tree, very well. Suppose if I have a node like this and two other nodes will be connected for this. Okay. And for this again, we are going to connect two other nodes. Something like this representation is called as hierarchical representation. Okay. To represent the data in a hierarchical manner, we are going for this graph data, tree data structure. Best example, in your college days, if you see, so principal will be there, right? Principal will be there, and head of the department one will be there, and head of the department HOD2 subordinates for principal, and class teacher one. Okay, class teacher two, something like that. If you want to represent the data in this hierarchical representation, then we will always prefer which data structure? Tree data structure. That is the actual real-time application of tree data structure what we have. This is nothing but actual real-time application. Okay. And even we have graph data structure is there. Best example, consider, so we have some Hyderabad city is there. Okay, Hyderabad city is there, and somewhere Bangalore city is there. So I want to reach from Hyderabad to Bangalore. So do you know, in the meanwhile, you can travel with multiple cities, right? So like this we have, right? There is no one path, multiple paths will be there. You can travel by using any one of the path. Of course, we will choose always the shortest path. So based on the traffic area, or so many things are there. Do you know these kind of things? If I want to represent, I need to go for non-linear, because we can't give guarantee that every city will be there in a continuous. So one city will be there and another city will be there somewhere. We are going to connect these two with the help of link. Sir, it is something like linked list only. In the linked list also, we can't give guarantee. One node will be available here, one node will be available here. We have to establish the link. Okay, sir, this linked list concept only we are going to use in the trees and the graphs also. We can't use list concept. Okay, we can't use a tuple, or we can't use array to hold the data. But whereas coming to this stack, queue, linked list, these things we can use by using list also, right? By using array also we can implement. But this non-linear data structure, it is very hard to implement. Okay. So this is nothing but what is the technique that we have. Okay, I think you people understood what is mean by linear, what is mean by non-linear, and how these tree and graph data structures will comes under these non-linear data structures. Okay, is the intro for this tree and graph are clear, friends?
Yes, sir, clear.
Yes, sir.
Right, good. Now Deepak Singh, nothing I covered, just I have given the difference between linear and non-linear data structure. The points are there here. Linear means continuation memory locations will be there. Non-linear means random memory locations will be there that we are going to combine with each other. Beyond that, nothing. Okay.
The hash tables.
Hash table is a continuation memory locations only, because
Okay.
there we are going to use list only, right?
Yeah, sir. Okay.
Yeah. Now, so coming to this first one that we are going to discuss here is tree data structure. In this, we have multiple subtopics are there. So the first topic, first module which we are going to cover here is nothing but module number 1. We are going to see what is meant by tree data structure. Sir, maximum we are going to get only theory part here. And in the second module, there is one special tree is there with the name binary search tree. Okay, binary tree. So where we are going to perform the basic level programming concepts. And the third module is there with the name binary search tree. So the shortcut for this is nothing but BST. So another module, height balanced trees are there. There I am going to cover AVL trees. Okay, so these are nothing but 4 modules that I'm going to cover as a part of this tree. Still we have so many trees are there, like red black trees, okay, B plus trees, splay trees, like that, but all are comes under this AVL category only. Those are nothing but height balanced trees. We are going to use different approaches to balance the tree, but don't worry, at the beginning of AVL tree, I will explain what is mean by height balanced trees and how we are going to do this. Sir, you may feel bored for the first part, but please make sure it is a very easy. You need to put some more concentration. So completely theory part will be there here. You are going to study in detail information about this tree data structure. First point, as we discussed already, it is a non-linear data structure, because the memory allocation won't be there in a continuation memory. Then, sir, it is nothing but hierarchical. Okay, it is nothing but hierarchical. Okay, hierarchical representation. Okay, hierarchical relationship. I can say it is nothing but hierarchical relationship. Hierarchical relationship in the sense what just now I told in the colleges, we are going to maintain the hierarchical relationships. So then I can say in our easy terminologies, relationship between parent and child. Okay, the relationship between parent and child is always considered as treasure. Okay, so where parent node will be there, under that a child is going to be attached. So first parent, it's a child, first parent, it's a child, like that. It is a relationship between parent and child. Okay, now, so next and after that, so here I can say each node, okay, each node, I'm talking with respect to linked list. So each node is connected to another node. Okay, each node is connected to another node by using edges, or another node by using edges. Okay, sir, if you want just one simple example, I told already one example. Suppose if you take this is nothing but one node, this is nothing but another node. So how these nodes are connected with each other? What is the link between these? This is nothing but the link, like the line which I am drawing. So here I can say this is nothing but a parent, this is nothing but a child 1, this is nothing but a child 2. Like how many childs we can declare? It is completely our choice. Okay, so here every node, this I am calling it as a node. Every node is connected with the help of edges. Okay, next and after that, sir, we have so many data structures are there, but how this particular tree data structure is going to be helpful, or how this graph data structure is going to be helpful? Very simple. The main intention for this is nothing but to make very efficient search operations. Okay, so it is the best suitable. Okay, I can say, so this is nothing but the best suitable. Best suitable for which operations? Search operations. Already we have different types of search algorithms. Like if you see, linear search is there. Linear search is going to take how much time complexity? Big O of n, because we required n comparisons. So, and even we have seen hash table also. It is going to take a big O of 1. But the problem with the hash table is nothing but we need to write a good hash function without any collisions. We have to write, suppose if you are writing with the collisions, definitely hash table is also not that much good. So then the technique what we have here is nothing but a binary search. So here it is going to take how much time, sir? Login. But already we covered this binary search algorithm. Do you know the hidden principle under this binary search is nothing but this binary search tree only. Internally it uses which concept? Tree data structure concept only. Okay, so how it is going to be happen? Suppose there is one property is there. I'm going to take one binary search tree. Listen carefully. So this is nothing but one example for binary search tree, sir. Now consider I want to search for an element. So consider I am giving key is equal to 9. Do you know? First we will compare this element with root element. What is the root element? 5. What is the element that you are searching? 9. You need to check whether it is equal or not. If it is not equal, don't see in the left side. Don't check. Definitely, if the element is greater than this root node, it will be available here. Then go for immediate left right child. Okay, immediate children. 7, right? What is the relationship, sir? When compared with 9, 7 is very small. That means it is available in the right side. Now you can check what is the relationship. Equal, right? So search is successful. How many comparisons? So 2 comparisons, since the number of levels are 2, like that. So in every time we are doubling the levels, right? If you see, in the 5th node we have only one level. In 307 we are comparing with only one element. Like almost 2 comparisons we are reducing. This efficient searching algorithm is called as what? Binary search. So our tree data structure is going to give the best result in this case, right? Can you please confirm, is this basic introduction for this tree data structure, is it clear for you people, friends?
Yes, sir. Clear.
Sir, how can we say memory allocation is continuous?
We can't say, because we are not dealing with any memory locations here, but this list is continuous in memory locations only, right? Here we are not going to create continuously. For example, if I create a node called 5, next time we want immediately we want to create next memory location. So after some time we are going to create. We can't give guarantee that it will be in the continuation. We will make a link between those two. That is nothing but our main agenda. Okay,
Yes, sir.
clear everyone? Right. Now, sir, next and after that, I want to show you normal. Okay, normal tree versus binary tree. I want to show you normal tree versus binary tree, or okay, let it be programming tree, something like that, I can say. 1 minute, let me search. Now you can see, sir. I will show you some images. Yes. Sir, have you observed? We can consider this one as an example, sir. Just for our convenient purpose. So you can see here, sir, this is nothing but the general representation, or I can say the parts of the tree, sir. Okay, sir, you can see here, what are the different kind of parts that you can able to observe here. We have leaves are there. Okay, leaf nodes are there, and we have branches are there. Remaining things we can remove. Okay, not required. Okay, we have leaves are there, branches are there, roots are there, but this is completely different in the programming. First we will represent root, then remaining nodes are called as branches or leaves or something like that. Like this it will be attached. The topmost node is always called as a root, and remaining nodes are nothing but attached like this. So I can say it is a mirror image of our normal tree. How our normal tree looks like, in the same way it will be there, but completely reverse structure. For normal tree, the root will be there in the ground, but for our programming tree, our root node will be there at the top. Like this we are going to represent. And one more thing, so I want to give the exact definition of a tree. Okay, so I can say a tree is a finite set of one or more nodes, such that okay, a tree is nothing but a finite set of so one or more nodes, such that listen these properties very well. The first one is nothing but, so there is specially, okay, there is a specially designed, so there is one specially designed node will be there, so called as a root node. So there is one specially designed node will be there, and we will call that node as which node, sir? Root node. There is a specially designed node will be there, that name is nothing but what? Root node. Then second point, remaining, okay, remaining nodes are partitioned, into n greater than or equal to disjoint, okay, disjoint sets. Sir, for your easy understandable manner, just I will take some example. Listen carefully. Sir, can I take is it a tree? Yes, it is nothing but a tree. Why? Because how many nodes are there here, sir? Only one node is there. I am considering that node as a T0. Okay, there is one specially designed node will be there called root node. Compulsory root node should be there. Sir, what about its children? Remaining nodes are partitioned into n greater than or equal to 0 disjoint set. In this case, the number of children is nothing but 0. Sir, this one is also a tree, okay, where we have only one child is there. This is also valid. So here I can say this first node is nothing but a T0, and this node I am calling it as a T1. So this is nothing but as usual root node, sir. So how many children are there here? Only one children is there. Sir, like can I take a tree which is having so two children? No problem, we can take. In this case, so this T0 will act as a parent. This T0 will act as a root directory, I mean root, and this one are nothing but subtrees. Sir, is it mandatory that we have to take only two? No, you can take any number of nodes, no problem at all. You can take any number of nodes attached to this, no issues at all. Sir, this is nothing but the property what we have for tree. If you want to define any tree, then compulsory there should be one special node should be there, which is nothing but root node, and remaining nodes, how many nodes can be attached to that? Greater than or equal to 0. That means a tree can have only one child or two children or three children, like you can define any. This is nothing but what is the exact definition of a tree. A tree is nothing but what? Finite set of one or more nodes, such that there will be one specially designed node will be there. The name of the node is nothing but root node, and remaining nodes are partitioned into n greater than or equal to 0 disjoint sets. Can you please confirm everyone? Is the concept is clear for you people, friends?
Yes, sir.
Please confirm everyone. Right, friends.
Yes, sir.
Right. Now, sir, almost that's all about the tree actually, tree data structure. But I need to give some important words, which is very, very important. So tree data structure terminologies. Sir, what are the different terms that we are going to use while taking a tree, sir? These are very, very important. Please listen carefully. The first term what we have here is nothing but root. Sir, what is mean by root? It is nothing but I can say it is a unique value. Okay, it is a unique. It is a unique node, or it is a unique node. Okay, so having only outgoing, okay, having only outgoing edges. So means what? It is a unique node which is having only outgoing edges. So here we can hide this where we are getting. Right, okay, let it be. Sir, here just for our convenient purpose, I am drawing a tree, sir. Please listen carefully. I think better we can go with our own tree here itself. Yeah. So have a look once. I have one specially designed node will be there. So that is called as what? Root node. Just for our convenient purpose, I am drawing a tree diagram here. Please try to understand. For all these tree examples, I am going to use this diagram only. Okay, this is nothing but one node. The name of the node is nothing but consider A. And it is having three children. The first children is nothing but B, and the second children is nothing but C, and the third children is nothing but D. The third child is nothing but D. And for B, sir, again we have three children are there. One is nothing but E. So another one is nothing but F. So another one is nothing but G. So what about D, sir? For D, we have one more children is there, which is nothing but H. And for E, we have another child is nothing but I. Like this we have. Sir, total how many nodes are there? I think 4, 5, 6, 7, 8, 9 nodes are there, sir. Now I am talking about the first node, which is nothing but a root. So there will be a unique node in the tree, which is having only outgoing edges. That means the edges should go from that. Sir, you can see here, is B is having only outgoing edges? No, it is having incoming as well as outgoing. So C is having incoming, but there is no outgoing. So D is having incoming and also outgoing. So like we have different nodes are there, but there is one unique node is there called A. You can see there is no incoming edge for this but we have outgoing edges are there. Do you know this is called as a route? Okay, this is called as what? A route. Now I'm going to talk about node. This is with respect to programming point of view, sir. I can say this is nothing but a fundamental, okay, a fundamental element of a tree. If you take any tree, it is nothing but a fundamental element. So each node has the following, three fields. Sir, what are those three fields? The first field is called as a data field. Okay, field is called as a data field, where it is going to store actual information. Second one is nothing but a special pointer. Okay, I can say that is nothing but left pointer. So left pointer pointing to left child. And the third one is right pointer, so pointing to right child. Like this we have. So if you want the same diagram here, just for your understanding purpose, I am rewriting. Please listen carefully. I am going to write in red color. Please listen, sir. Here consider, just I want to represent A, sir. Okay, I want to represent, or let me take D. I want to represent D. If I want to represent D in the double linked list format, we have to represent. Okay, in the double linked list format, we have to represent. Sir, what is the content here? The content is nothing but D. What is a left node for this? Do you know? Left node is again having, okay, another node with left and right pointer, and content is H. Is there any left node for H? No. That's why we are going to keep it as a none. Is there any right node for this H? No. That's why none. Is there any right node for this? No. That's why it is going to point to none. Like this, do you know this terminology? Already we have seen. This terminology is called as what? Node. In our linked list, we used node structure in this style only. Can you please confirm everyone? Is this concept is clear for you people, guys?
Yes, sir, clear.
Is these two terms, like what is mean by root and what is mean by node, is these two terms are clear?
Yes, sir.
Please confirm, friends.
Yes, sir.
Right. So now I will represent few more definitions. Please listen carefully. These terms are important, sir. I'm going to keep the diagram as it is. Okay. So the next term what we have here is edges. Edges. Sir, what is mean by edges? Very simple. It is also a fundamental. It is also a fundamental. Okay, a fundamental part of a tree. Okay, and it is used to connect. It is used to connect two nodes, sir. It is used to connect two nodes. Example, sir, can I say AB is nothing but an edge, AC is nothing but an edge, AD is nothing but an edge, BE is an edge, BF is an edge, BG is an edge, DH is an edge, EI is nothing but edge. That's all. These are nothing but edges which are present in the tree diagram. Next, and after that, I want to talk about one more word called path. We are going to write a program also to print all the paths. Okay, path means what, sir? An ordered list of nodes, so that are connected. Okay, that are connected by edges. Edges are called as a path. Best example, sir, I'm going to ask, what is the path from A to I? Okay, so if anyone is asking what is a path from A to Z, A to G, sir, if I want to go to A to G, first we need to go to A to B, and from that B we have to go to G. Or if anyone is asking what is a path from A to I, so what is the path, sir? A to B we have to travel, and B to E we have to travel, and E to I we have to travel. So what is mean by edge and what is mean by path? These are very clear for you. Next term, leaf nodes. Sir, what is mean by leaf nodes? Very simple. The nodes which are not having any children. Okay. The nodes which are not having any children. Okay. Any children are called as leaf nodes. Leaf nodes are the nodes without outgoing edges, without outgoing edges. Sir, can I say in this tree, sir, is I is a leaf node? Yes, because we don't have any children. But don't tell E is a leaf node, because for E we have one children is there. So F is a leaf node, G is the leaf node, H is the leaf node. Okay, so C is the leaf node. These are nothing but the leaf nodes which are available. Sir, can you please confirm what is mean by edge, what is mean by path, and what is mean by this leaf node? Is these terms are clear for you people? Please confirm.
Clear, sir.
Yes, sir.
Right. Right. So now we have to see one more example, one more terminology here. So height of the tree, sir. What is the height of the tree? The general name itself is indicating how many levels are there. So height of the tree, okay, height of the tree is a sum of edges on the longest path between so root and leaf node, root and leaf node. Sir, if you take root and leaf node, sir, in these root to leaf, so which are root to leaf? AI is the root to leaf, AF is the root to leaf, AG is the root to leaf, AC and then AH. These are nothing but root to leaf, right? But in these, which is the maximum depth, sir? So we can say A to I, because that is the having the longest path. I can say height of the tree is nothing but how many edges are there. So from A to I. So A to B one edge is there, B to E one edge is there, E to I one edge is there. I can say the height of this particular tree is nothing but 3. Maximum 3 edges are there from root node to leaf node, sir. Hence we can say this is nothing but height of the tree. Okay. So next and after that, sir, I need to consider level of the tree. Sir, please concentrate these terminologies, because in the programs we are going to use these. So level of the tree. What is mean by level of the tree? So the level of node or tree is number of edges on the path from root to that node. Suppose, sir, I want to see A node is available at which level? Sir, from the node A to node A, how many edges are there, sir? There is no edge. I can say it is available at 0th level. So do you know this B comma C comma D? These are available at level 1. Sir, why? If you want to move from B to C, okay, sorry. If you want to move from A to B, how many edges are connected? 1. So A to C, 1. A to D. I can say this B and C and D are available at level 1. Sir, what about E, F, G, H? If you see, to move to these, compulsory you have to use 2 edges. Sir, what about I? It is available at what level, sir? It is available at 3rd level, because 3 edges you have to transfer. Sir, in your shortcut, if you want to understand, this is always at level 0. This is always at level 1. This is always at level 2. And this is always at level 3. Like this, we have to consider. Can you please confirm how to calculate height of the tree and how to analyze level of the tree? Is these two words are clear?
Yes, sir, clear.
Yes, sir.
right? Good. So now the next one, still few more definitions are there. So the next definition is parent. Sir, we know very well about this word, no need to cover in detail because parent means right? So which one will be considered as a parent? We know. Parent means the node which is having its children are always called as parents. Okay, let me define that. Sir, what is mean by parent? A node is a parent of all the children. Okay, of all the children, so that are linked by outgoing edges. Sir, parent means what? That are linked with another children by using outgoing edges. In this example, sir, which are parents? A is not a parent because it is a root node. Can I say B is a parent? Yes, because it is having the children. Okay, so this is nothing but, one second. So this is nothing but B is a parent because it is having children. Sir, can I say C is a parent? No, it is not having any children. Sir, D, yes. One second, sir. Yeah, sorry, sir. I can say this B and D, these two are nothing but what? Sir, parent or not? Yes. Sir, why those two are considered as a parent? Because as you can see, for this B we have children and for this D we have children. And even E is considered as a parent. Okay. Sir, do you know A is also parent? Because A is having some child, but A is both the parent as well as a root node. Okay, like this we have. Sir, what is mean by children? What is mean by children? You know very well that node which is taking the edges. Okay, the nodes that are having incoming edges. Okay, or we can consider as children. Sir, can I say is B is a child? Yes, B is a both a parent as well as a child, sir. Can I say C is a child? Yes, definitely. Sir, D is a child. Yes, E, F, so G, okay, H, and then I. Except root node, we can say all the remaining nodes are nothing but children only. Okay, already we covered this particular terminology also. Sir, there is one more term is there with name siblings. Siblings. Sir, what is mean by siblings? Very simple. The nodes in the tree. The nodes in the tree that are children. Okay, that are children of the same parent. That are children of the same parent. Okay, are called as siblings. Sir, in this example, sir, can I say B, C, D are siblings? Yes, because for B and C and D, we have a common parent is there called A. Sir, E, F, G, for these three, a common parent is there called B. But H, we have only one parent is there. So we can talk about these siblings when we have more than one child. Can you please confirm? Is this parent means what? Children means what? This sibling means what? Is these three terms are clear for you people?
Yes, sir. Clear.
Yes, sir. Clear, sir.
Right. Sir, next one, which is very, very important. Sir, I am going to talk about degree of a node. Degree of a node. Sir, what is mean by degree of a node? The total number of subtrees. The total number of subtrees attached. The total number of subtrees attached to that node is called as degree. Okay, degree of the node. Sir, best example, I want to find out, so degree of the node A, sir. Sir, what is the degree of node A? How many subtrees are attached, sir? 3. So
Three.
what is the degree of B? Tell me what is the degree of B?
3.
3. So can you tell me what is the degree of C?
0.
Good. 0 is nothing but a degree. So what is the degree of D, sir?
1.
1. So degree of any node, we can call it as, so how many nodes are connected to that? How many outgoing edges are there? You can find out. That is considered as a degree of a tree. Similarly, sorry, degree of node. Similarly, degree of a tree is also available. So what is mean by degree of a tree? The total, okay, or I can say maximum degree of all nodes is called as so degree of tree, sir. Maximum nodes are called as a degree of tree. Sir, can I say the degree of this particular tree is nothing but maximum nodes? Maximum, I think 3, right? So 3, I can say the degree of the tree, sir. Can you please confirm? Is this terminology is clear for you people?
Yes, sir.
Degree of a node and degree of the tree. Good. Now, so next 3 more definitions are there. Have a look once. What is the next definition is, sir, ancestor. Very, very important. Ancestor. Sir, what is mean by ancestor? Very simple. A node. Okay, a node reachable. Degree of the tree is nothing but you need to find out the degree of every node present in the tree. Deepak Singh, suppose if your tree is having some 5 nodes are there, for every node you have to find out the degree. Okay, among those 5 nodes, which node is having highest degree, that will be considered. Got it? Right. Sir, what is mean by this ancestor? Very simple. Sir, a node reachable, a node reachable, a node reachable. So through a node reachable through repeated, okay, repeated moving from child to parent. A node reachable from repeated moving from child to parent are called as ancestors. Example, who is the ancestor for I? Sir, try to move from this particular location to the root node. Among that, we are going to get E, B, and then A. I can say E, B, A are nothing but ancestors for the node I. Okay, like parent, like that. Then there is one more term is there called predecessor. Okay, predecessor. Sir, what is mean by this predecessor? What is mean by this predecessor? Very simple, sir. So while displaying, okay, while displaying or while traversing or while visiting, if any node comes, before another node, so then so that node is called as a predecessor. Okay, predecessor of that node. Anyway, we will see some example, then you can get a clarity. Sir, E is, okay, so E is predecessor. Okay, E is okay, so E is predecessor. Okay, predecessor of I, sir. That means if you want to go to I, first we have to visit E, right? Next to the E is nothing but I. So that means when you are moving, if any node comes before that, then I can say that node is nothing but a predecessor. Don't get confused, sir. The node which comes first is always called as a predecessor. We have successor is there. What is mean by successor, sir? Same points, right? There is no change at all. But what modification? While displaying or traversing or visiting, if any node comes after another node, then we can say that node is nothing but what? Successor of that node. Sir, can I say this E is successor of B? Yes, because sir, you can see when E is going to come. So after B only, right? Then it is called as successor. So don't worry in detail about this. In the applications, I will explain. Can you please confirm, is this predecessor and successor are clear for everyone?
Yes, sir.
Yes, sir. I have a doubt in ancestor.
Hmm.
Ancestor. Sir,
Hmm.
can you please show the definition? Ancestor. Like you have taken I. No. At the below. Yes. Here you have taken I, E, B, A. Okay. So that is
Hmm.
fine. But what about F? What F and C are ancestors or not?
F1?
C.
No.
Okay. So that
Because
means that
it should be there from the link. Link should be there.
okay, direct link.
Direct link should be there. Because you can see F parent is B, B parent is A parent, like that you have to reach up to root. Okay.
Okay.
So whatever nodes that you are getting in that, you have to print those nodes.
Okay.
You should not come from the root. You have to go from the bottom.
Oh. Okay, sir. Clear.
Please confirm, friends, is these terminologies are clear for you people?
Yes, sir.
Because if you are okay with this, we will go with programming. Right. So with these, the first module, what we have, the basic definition, total theory part, whatever we have for this tree data structure got completed. Now we know what is meant by tree and the terms which we are using in the tree. So now my next topic, that is the next module here, is binary search. Today we are going to do post-mortem on this binary tree. Today complete class is about binary tree only. Sir, don't feel that it is difficult. Whatever concepts that we have learned till now, if I apply that, it will become very easy. I will explain slowly. Please concentrate. Sir, what is mean by binary tree? Very simple. Binary tree is a type of tree. That's we know. Binary tree is nothing but a type of tree in which, okay, in which each node has at most two children. Okay, at most two children. At most two children means what? It can have either 0 children or 1 children or 2. That's all. Not more than 2. Not more than 2. Sir, which are referred as the left child, which are referred as a left child and a right child. Okay, which are referred as left child and right child. If you want more detailed explanation, so in binary tree, so each node will have, okay, one data field, one data field, and two pointer fields pointing to left subtree and right subtree, like this we have. Sir, if you want, just I will try to explain just the basic what I can call terminology. Listen carefully. Sir, I have a node is there. Can I say, is it a binary tree? Yes, it is the binary tree, because so it is having only one root node is there. There is no left child. Sir, in Python, I am representing that as a none. So right child is also not there. I am representing it as a none. Sir, can I take a single node which is having only one left child? 1 second, please wait. Yeah, right. You can see we have only one left child is there, sir. But I don't have any right child. Simply it is pointing to none. Sir, is it a child? Yes. Is it a binary tree? Yes. Now I have a binary tree like this where I have left child is not there. But I have right child is there. Is it a binary tree? Yes. Sir, I have a node is there. For that left child is available. Right child is available. Is it a binary tree? Yes. Sir, I have a node is there where it is associated with 3 children. First of all, yes, it is a tree. Okay, we can say it is a tree, but it is not a binary tree because what is the property of a binary tree? So it must
Not more than
have
two.
2 children, at most 2 children, means either 0 or 1 or 2. So like that, we can able to implement. You may have a doubt, sir, for tree data structure directly, why we are not covering any programs? There is a problem is there. Why? Because we don't have a limitation of the number of children for the tree, right? That's why we can't do any operations on the tree. So there should be some constraint. So we can perform any type of operation on this binary tree. Sir, how this binary tree is going to be implemented? Suppose if I have 10 nodes are there, first I will create a root node and I will create a left node and I will go for right node. And for that left, again left node, right node, like that until you are getting all the elements we can create. That kind of flexibility we can do that. So this is nothing but what is the exact definition of a binary tree. So when a tree is said to be binary tree, I think there is no complexity here. You people understood the basic terminology. Clear, friends?
Yes, sir.
Any doubts?
Yes, sir. Yes.
Clear, right? Right. Next. So very important. Now we are entering into the programming. Sir, binary tree. Okay, binary tree representation. Sir, how you can able to represent a binary tree? Let us see. So here there are two ways are there. Okay, there are two ways are there to represent. Okay, to represent binary trees. Not only binary tree, any kind of tree. The first one is nothing but sequential representation. Sequential representation by using list. Second one, sir, we can use linked list representation. Okay, by using which link, sir? Double linked list we can represent. Anyway, for binary tree, I'm going to use sequential representation only. But for what you can call AVL tree and binary search tree, we will go with linked list. Or here also I will explain at least one program. Sir, how you can represent in a sequential? Very simple. So in this sequential representation, if a node is present at a nth position, nth location, okay, so n is nothing but I can say root or parent, okay, I can say better to go with the parent. Sir, do you know parent node is available? Parent node is available in nth position. In nth position means, so do you know its left child? If its left child is available in 2n plus 1 position. and its right child will be available in 2n plus 2. Based on this formula, we can represent a sequential way, sir. So best example, consider I'm going to take a list. Okay, I'm going to take a list. So where the elements are arranged like this. Okay, 1, 2, so 3, okay, 4, 5, 6, 7. Like this I'm taking just for our convenient purposes, sir. Okay, now listen carefully. How I'm going to draw this diagram is, first I am taking 1 here. Its left child is nothing but 2. Its next child is nothing but 3. Its 2 left child is nothing but 4. Sir, 2 right child is nothing but 5. 3 left child is nothing but 6. 3 right child is nothing but 7. Sir, how you are drawing very perfectly? Because I am moving from top to bottom and from left to right. So first element root node, next element left to the root, next element right to the left. Sir, is there any chance to fill the data? No. Then immediately the next value will become like this. Like this we have to represent. Sir, for your convenient purpose, please listen carefully. I am going to give the locations 0, 1, 2, 3, 4, 5, 6. Now consider I have an object is there, sir. Okay, I have n value is equal to something like I have 0. Please concentrate well. For your understanding, I am giving the positions 0th location, first location, second location, so third location, fourth location, fifth location, sixth location. Now, which is the element present at 0th location, sir? In 0th location, we have 1 is there. In the table, in the 0th location, 1 is there or not? Yes. Sir, what is the left child of this 0, sir? Can I say 2n plus 1? If you substitute 2 into 0, that is 0 plus 1, which is nothing but 1. The node which is available at first location is left child of 0th node. Sir, I want to find out right child of 0th node. Can I say it is a 2n plus 2? Sir, which will become 0 plus 2, which is nothing but 2. Sir, the data which is available in the second position is nothing but it's a next child. Sir, can I take next example? Like let me take n is equal to 2. Sir, what is the node present in the second location? 3. I want to find out left child for this second position. Sir, 2n plus 1. What is a 2n value? So 2 into 2, 4 plus 1, which is nothing but 5. So the element which is available at the fifth location is the left child of 3. Right? Right child of second location. Sir, 2n plus 2. Okay. So 2 into 2 plus 2 I am taking. 4 plus 2, 6. The element which is available in the sixth position is nothing but that particular element. Like that we can go, sir. I think how to represent this tree diagram, okay, in sequential list format. Is it clear?
Yes, sir, it is clear, but binary tree means we can also have one node. So in that case, it will be failed now. For example, if we are removing sixth node, like fifth index node, third left. So in that case, my seventh value is present at fifth index, then it will be failed now.
Yeah. This is the problem what we are going to face with binary trees.
Yeah.
Okay. In the binary trees, completely you have to fill the data from top to bottom and from left to right. Okay. So such a type of trees are called as complete binary trees. I will explain that part. But as of now, consider we have all the data is there. Suppose if 7 is not there, then we can happy. But in the middle, we can't delete the data. Got it?
Yes, sir. Yeah.
Please confirm everyone. Is the concept is clear?
Yes, sir.
Any doubts up to this? Right. What is the next one here? We have linked list representation is there. Sir, how to represent this in the linked list? We know very well we are going to use a double linked list concept to represent this. Okay. So we can use double linked list, or we can use a double node structure to represent to represent so binary trees in linked list format. Sir, the same diagram, just I am going to rewrite in blue color. So I am going to represent like this. This is nothing but one node. So the content is nothing but one. And next left node for this is nothing but we have 2 is there here. And right node for this is nothing but we have 3 is there here. And for 2 left node is nothing but we have 4 is there here. And for a right node it will become 5. And for 3 its left node will become 6 and its right node will become 7. Like this we have. So its left node is pointing here, its right node is pointing here, and its left node is pointing here, and its right node is pointing here. Its left node is pointing to none, its right node is pointing to none, none, so none. And here I am going to take its left node is pointing here, its right node is pointing here. This will point to none, and this will point to none, and this is pointing none, this is pointing none. Like this we can represent which one? The linked list tail. Anyway, I will explain in the program. There you people are going to get a clear clarity, sir. Can you please confirm, is this concept is clear up to this whatever I covered, friends?
Yes, sir, clear.
Right.
Yes, sir.
Right. But if I want to understand these terminologies very clearly, so displaying the list, all these things will become very easy. But the toughest part what we have here is so displaying the tree, binary tree traversals. Okay, so there are multiple traversal techniques are there. We are going to see here. Top level 3 traversals are there, sir. Okay, just I will give break for some 10 minutes and we will continue. Okay, so break for 10 minutes, go and refresh and come, we will continue. We have some programs are there, easy programs only. For first 10 minutes you need to understand the concept, then implementing the methods will become very easy. Okay, so go and refresh and come. Right. Welcome back. Can you please confirm, sir? Am I audible? Is my voice is clear?
Yes, sir, it's clear.
Yes, sir.
Right. So the next concept what we are going to discuss here is binary tree traversals. Sir, what is mean by binary tree traversals? So traversing the tree is nothing but visiting or displaying each node, okay, so present in the tree, okay, so once each node present in the tree once, okay. So the following are the various methods existed for binary tree traversals. So do you know these traversals are safe for binary search tree, for AVL tree, for any kind of tree. That's why here we are going to concentrate only on binary tree traversals. In the remaining applications, we are going to see this. So like this only, there is no modifications. That's why in binary search tree, all these things, I'm not going to cover these traversals. So please concentrate here itself. And sir, there are three traversals I told, right? The first one is nothing but what? In order traversal. And the second one is nothing but pre-order traversals. So third one is nothing but post-order traversals. Like this we have. Sir, here we have root node will be there. That I am going to represent as a D. And the left node is there, right? That I am representing as a L. And right node is there, right? I am representing as a R. So in the in-order traversals, first we have to visit. Okay, first we have to visit left subtree. Then we have to visit root node. Then we have to visit right subtree. LDR. First left subtree, then root node, and then right subtree. Sir, what about the pre-order? First root should come, then left and then right. DELR. First root should come and then left and then right. Sir, what about the post order? So LDR. That means root should come at the last. Left node I am taking, right node I am taking, and then root. Like this, there are three traversals are there. Sir, we will see examples, then only you can able to understand these terminologies very clearly. So let me take example number 1. So I will show you the diagram. So we have to find out what is the in order for that, and we have to find out what is the pre-order for that, and you need to find out post order. First example, a basic example I am taking. Consider I have a root node is there called A, and its left subtree is nothing but B, and its right subtree is nothing but C. Like this we have. Its right subtree is nothing but C. Now we have to find out in order. In order means what? First we have to visit left subtree. In the left subtree, we have only one node is there, which is nothing but B. And in the root node, which we have A, and right subtree is having C. BAC is nothing but in order for this particular tree diagram. Sir, I want to find out pre-order. Pre-order means what? First, we have to visit root node. In this tree, what is the root node A? Then we have to visit left subtree, which is nothing but B. Then we have to visit right subtree, which is nothing but C. So what about post order? First, we have to visit left subtree, which is nothing but B. Then right subtree, which is nothing but C. At last, we have to visit the root node, which is nothing but A. Like this, we have to take. So I think this first example is clear for you, right? If you are okay with this, I will explain one more example for you to better understand. Please confirm, is this first example is clear for everyone?
Yes, sir, clear.
Yes, sir.
No. Second example I'm taking almost same tree, sir. Just I'm going to do small modification. Please see that modifications. I'm taking A as the root node. Okay. So then the left subtree will become B and right subtree will become C. But I'm not going to stop here. So B is having again the children, okay, like C and then D. Let it be C and then D. Oh, already we have taken C. Okay, no problem. Here I will take C. Okay, here I will take D. C, D, E. C, D, E. Like this I am taking. So for this, we have to find out in order and then pre-order, post-order. Please listen carefully. There will be some small twist will be there here. Sir, look into this. We have to find out in order. In order of this tree or not? Yes. In the in order, what is the first step? We have to visit left. But unfortunately, this left itself is again a tree or not? Yes. You need to apply for this first. So in order means what? First we have to visit the left subtree, which is nothing but D, and we have to visit the root node, which is nothing but B, and we have to visit right subtree, which is nothing but E. So do you know this is nothing but, so for the main tree, if you take left subtree, in that left subtree, this is nothing but the concept what we got. Then after visiting left, then as usual left is visited. So what is the missing node here? A, right? That is nothing but root node. And then we have to visit right subtree. This is nothing but in order. So while visiting, if left subtree is having again a tree, you have to apply the same principle again. That is the concept I explained. Let me take a pre-order here. What is mean by pre-order? Sir, in the pre-order, first we have to visit root node. Sir, what is the root node here? A. Then we have to visit left subtree. But left subtree is again is having a tree. In that you have to apply the same DLR principle. In this, what is the root node? B. Left subtree D. Right subtree E. So root node completed, left subtree completed, and remaining right subtree is there, right? That is nothing but C. Okay. Sir, now post order. Post order means what? First we have to visit left and then right, at the end root node. Sir, what is the left subtree here? Again it is a tree. In that again apply LDR. In that left subtree is nothing but what? D. Right subtree is nothing but what? E. Root node is nothing but what? B. Okay. So again, sir, first node left subtree got completed. Then we have to visit right node, which is nothing but C. At last take the root node. Like this we have to take. Right? I think second example, it is clear for you people. Right? Please confirm any doubts up to this.
No, sir, clear.
No, sir, clear.
Everyone please respond clear up to this, whatever I covered.
Yes, sir.
Right. Let's go with one more example so that you can able to understand very clearly. What is the next example that I'm going to take? Similar kind of thing, sir. So we need to find out in order for this, and we have to find out pre-order for this, and we have to find out post order for this. Let us see. Sir, first one is what? We are going to take the root node as a. And for this left subtree is nothing but I am taking B. And for A, right subtree is nothing but C. And for B, we have another left subtree is there called E, sorry, F. I think better we can take D. Okay, let it be. and here I am going to take D and then E. Like this I have. Sir, we need to take, okay, we need to take in order first. In order means what? First we have to visit left subtree. Left subtree means what? We have this B and then F. Since it is again a tree, again visit left. What is the left here? F. Sir, then we have to visit root node, which is nothing but B. Do we have any right child for this? No. So left subtree got completed. Then visit root node, that is nothing but 8. Sir, what about right subtree? Right subtree is again is having a tree. Then we have to visit again left subtree D, root node C, right subtree. Sir, what about pre-order? First we have to visit left subtree. In that left subtree, again we have a tree. Visit left subtree, F. Root node, so B. Right subtree, there is no right subtree. Okay. Pre-order means first root node, right? So we have to visit A. Then left part. In the left part, again we have another tree is there. Visit root node. Then go to left and then right. There is no right. And main root is also completed. Go to the right part. Right part is again having a tree. Then what we have to do? Visit left subtree. That is nothing but a D. And first we have to visit root node, then left subtree, then right subtree. What about post order? First we have to visit left subtree B and then F. In that again left means F, then right node, we don't have any right for that, and root node, which is nothing but B. Left part completed. Then go to right part. In the right part again we have a tree. In that first visit left, so then visit right, then visit root node. So left part of the main tree completed, right part of the main tree completed. Then we have only one node is there, that is nothing but root node. This is nothing but the third example what we have. Can you please confirm, is this example is clear for everyone?
Yes, sir.
Yes, sir, clear.
Yes, everyone please confirm. Right. So now you have to spell for this. I'm going to draw one more diagram. You have to tell the correct output for this, because we need to check this in the program. So in order and pre-order and post order. Sir, what is the tree that I'm going to take here is, I have the root node as a 1. Its left child is nothing but 2. Its right child is nothing but 3. For this left child is nothing but 4. For this right child is nothing but 5. For this left child is nothing but 6. For this right child is nothing but 7. Sir, one small request. Can I write this node as a list of values like 1, 2, 3, 4, 5, 6, 7? So if you want, you can check. Is it in the proper format or not? Yes. Can you please confirm, is the diagram and the representation which I have represented in the form of list are clear?
Yes, sir.
Is it correct?
Yes,
Please
sir.
confirm. Right. So now slowly I am going to convert into program. Please concentrate well. Sir, what is the in order for this? First, we have to visit left subtree. Left subtree is again having a tree. That's why in that left is nothing but 4. I will give space for separation. Then root node, then right subtree. So left completed, root node is 1, right we have to take. Again left subtree, root node, and then right subtree. Sir, what about pre-order? In the case of a pre-order, we are going to take first root node, then left subtree. In the left subtree, again root node is 2, right subtree, left subtree, right subtree. Then if you take a right subtree, so 3 is the root node, 6 is the left subtree, 7 is the right subtree. If you take post order, okay, so first we have to visit left subtree. In that again left subtree is there, so 4 will come, then right subtree and then root node. Sir, then we have to visit right subtree. Again it is having a tree, that's why 6, 7, 3 and at last 1. Sir, please remember, always the root node will come in the beginning in the case of a pre-order. Always the node will come at the ending in the case of post-order. In the case of in-order, it will come in the beginning, sir. Can you please confirm for this diagram, is this concept is clear?
Yes, sir.
Yes, sir, clear.
Yes, sir. Clear.
Now, last example. You have to tell answer for this. If anyone is having paper and pen, please practice parallelly. A big diagram I'm going to take. Example number 5. And here the list which I'm giving is, so 1, 2, 3, 4, 5, 6, 7, 8, 9, up to 10, 11, 12, 13, 14, 15. Like this, I'm taking a big list, sir. How the diagram will be better, I will erase this diagram and we will write a new clean neat diagram. Have a look once. So the root node is 1. Okay, its left subtree is nothing but 2. Its right subtree is nothing but 3. Okay, first level completed. For 2 again we are taking 3, we are taking 4, and for 3 we are taking 5 and 6. And for 3 we are taking 7. Okay, next 8, and here we are taking 9, and we are taking 10, and for this we are taking 11 and 12, and for this we are taking so 13 and 14. Somewhere 3 I repeated, right? Yes, here we are going to get 13 and 14. So here 11 and 12. Next we are going to get 9. So 1, 2, 3, 4, 5, 6, 7. So 8, 9, 10, 11. So 12, 13, 14, 15. So this is the diagram what we have. Sir, is the diagrammatic explanation, is it clear?
Yes, sir, clear.
No. So we need to construct in order, pre-order, post-order for this. Okay. Yeah, please tell me what is the in order for this.
8, 4,
8, 4, 9,
1 second.
9, 2,
8,
4, 9,
8, 4,
9,
9,
2,
2,
10,
10,
10,
5,
5, 11, 11,
11,
1,
1,
oh,
12,
12,
6, 3, 6, 13,
6,
13,
13,
3,
3, 14,
7, 15.
7, 15.
Very good. So like this we have. Now we need to see, okay, we need to see what is the pre-order for this. Pre-order means what? First we have to visit root. Root node is 1. Then left subtree. Left subtree, you can see here, left subtree is again having a tree or not? Yes. So then what we have to do, in the tree, root node is 2. Sir, again left subtree. It is again having a subtree. That's why 4 is the root node. Then we have to take a left subtree and then right. Main left completed and right is there, right? So in that again we have to take a root node in the beginning. So then we are going to consider, okay, a left subtree and then we have to consider a right subtree. Is it correct?
Yes, sir.
So 1, 2, 4, 8,
11.
9, 5, 10,
11.
and then 11.
Yeah.
Okay. So main root node completed, left part completed, right part. In the
Three.
right part, again, we have to start from 3 and
Six.
then left subtree is nothing but again a tree. So 6, we have to
12,
take a 12 and
13,
13.
7,
So then
14, 15.
7 and then
14, 15.
14, 15. Like this we are going to get. Let me take post order. So first we have to visit left part. In that left part, again left part. In that left part is nothing but 8,
9,
right
4.
part is 9,
4.
and root node is 4. Left part completed. In the right part, again a subtree.
11.
So left and then right and then
5.
root. So total left and right completed, root node
2.
is 2. Then go to right subtree. Again we have a subtree. In that left part, in that
12,
again
13,
left
6.
part, right part, and then root node.
14,
Then
15,
again
7.
14. So
15,
15
7.
and then 7 and then
3,
3
1. 1,
and
1.
then last one.
Yes.
This is nothing but in order, pre-order and post order what we are going to get. Sir, if you are clear with these terminologies, I will directly go for the programming now. So step by step I will explain. Is this concept is clear?
Yes, sir.
Yes, sir. Clear.
Please confirm everyone. Is the concept is clear up to this whatever I covered? Right. Now observe carefully. I am going for the programs. It is a very simple, sir, not that much complicated. So my first program is nothing but creation. Okay, creation of a binary tree. So creation of binary tree. How to create that? We have multiple ways are there. What is the first way that we have creation of a binary tree? By using list concept, that is sequential representation I am taking. Sir, for our easy understanding purpose, I will take this one. By using this, I want to convert a list. Let us see, sir. This is my list, right? Okay, this is my list what I have. So from this, we need to construct a node, I mean a tree. So for that, I am taking a class called a tree. Okay, I am creating a class called a tree. Compulsory, we have to represent the data in the form of node only. So I am taking a constructor. I am taking a constructor which is going to have data field, and left pointer will be there, which is always none. Right pointer will be there, which is always none. And whatever data that you are giving, that will be created with a node, and whatever left pointer is there, that will be always pointed by the left whatever you are giving. If we are not giving, then what will happen? It will take the default value as a none. This is nothing but node class. Sir, we don't have any option. We have to use only this node class to represent this. And coming to the tree, I'm going to construct an empty tree. Whenever you are creating a tree, immediately one root node I am going to assign. Initially, we don't have any elements, right? That's why I'm creating a root node is equal to none. Now we are going to create a root node with none. Sir, now what will happen? If I'm creating a new tree, first step, what will happen? A new root node will be created. A new root node will be created. That root node is always pointing to which value, sir? None. Like this we are going to get. Don't worry, slowly I will explain the process how we are going to create. For that, I'm going to take one function. What is that function? Is nothing but t dot. So create a tree. Just I will pass this list. Just I will pass this list. What is the function name? So create tree. Okay, create tree like this I am taking. Since we are writing within a class, we have to take self and one list we are going to pass. So self dot root is equal to, I am creating a new root node. For that, again, I am calling one more function called create tree utility function I am going to take. So this utility function is going to take a list and starting from which location we are going to create a tree. Like that I am going to take, and we need to write code for this create tree utility function. Okay, don't worry, how we are going to write this I will explain in detail. As of now I am putting empty. Sir, I created totally 4 things in this tree class. What is the first class? To represent the tree, I have taken a class node and I created one constructor. And in the second case, I created a constructor for the tree class where root node is equal to I am taking none. And we have to create a tree with self.root is equal to self.create a tree utility function that I am calling. That utility function is going to take a list and starting position because I don't want to supply the starting position while creating the tree. Okay, here simply I will give L, but a starting position, all these things I am not going to give. Sir, can you please confirm, is the structure up to this, is it clear?
Yes, sir, clear.
I request everyone to please confirm.
Yes, sir.
No doubts, right? Right. Sir, slowly I am adding some functionalities here. Please listen. What is the first functionality that I am going to add here? So we have to create, sir. To create the list, first I am trying to calculate what is the size of the list. What is the size of the list? Sir, this list contains how many elements? Almost we have 7 elements are there. Okay, almost we have 7 elements are there. Then current will always point to self dot node L of starting value I am giving. So means what? It is calling node function. That means this one, which is taking data field. Sir, is the data field is available or not? Yes. What is the starting value? 0. So 0th location, which content we have? 1. So it will create a new node. It will create a new node. Okay. 1 second. Yeah, sorry for the delay. Now you can see, sir, we are creating. So what is the size of the list? Length of the list. Current node is equal to self dot node. So we are creating a new node with starting position. What is the starting position that I have given? 0. In 0th location, we have 1. So it will create a node with the content 1. Sir, this node is represented by which one? Current node. Like this I created. What will be your previous field? That is, what will be your left subtree? Null. What about your right subtree? It is also pointing to the null. Now we have to calculate its left subtree and right subtree, right? Let me calculate, sir, my left subtree is, we have a formula. We have index value, right? 2 into start plus 1 will give left index. Right index is nothing but what? 2 into start plus 2. Now try to calculate left index. Sir, what is the starting value that we have given? 0. So 0 into 2, that means 0 plus 1 is equal to 1. And right index will become, so 0 plus 2, which will become 2. Like this we are going to get. Sir, identify which element is available at first location 2. Which element is available at right location 3. What is the size of the list? Sir, is it having 7 elements? Now you have to check. What is the condition that you need to check here is, if your left index, whatever you calculated, is less than the size, means what? We can put that value or not? Yes. So already your current is there. Its current left field is pointing to self dot. So create tree, I am calling utility function. So by passing the same list, and what about left index? That left index will become 1. That left index will become 1. That means recursion process I am going to do, sir. That means recursion process I am going to do. Sir, now what will happen? Now what will happen? So if R value is less than size, we have to create right side also, right? So your current dot right will become, so self dot create tree, I am taking utility L comma R. And once if these two things are completed, we are going to return current. Now see what will happen in this example. Left index, whatever we got is 2. Is it less than the size? Yes. Then immediately what will happen? It is creating a left pointer, which is pointing to the node 2, sir. Then again it is going to call recursively, and right node is pointing to the node which is having the element 3. Again it is going to call recursively, like how many times? Until your size of the index is going to be crossed. That's all. Nothing is there. We called initially created tree function. So from that I am calling utility, because we need to pass the starting value. That is the reason. So in the utility function, we are creating a node with a starting index value. By using that starting index, we are finding its left index value and right index value by using the predefined formula. If that index is there in the list, then corresponding element I am going to attach, and I will call this method recursively for the remaining indexes. Okay, because every parent will become child, right? Then immediately we are going to looking care of that one. Can you please confirm, is the creation of this linked list by using so normal list concept, is it clear for everyone?
Yes, sir, clear.
Do you have any doubts up to this?
Sir, where we can increment L and R value?
We are not incrementing. Why we have to increment? Because you can see this index value we have passed as a 0, right? By using this, we calculated what is the index of this one. What is the index of this one? We got 1.
Okay,
By using this, we got index of this one. This is L and this is R, and this is nothing but starting. Next time, this 1 will become your starting value. From that, we will calculate left and right indexes. Okay.
okay. Sir, it first completing left side and go for right side only, sir.
Yes. Left side, it will finish total creation of the tree. Then only it will go for right side.
Thank you, sir.
Right, sir. Clear everyone? Right. Sir, creation of the tree is okay. If I execute this program also, successfully our code is going to work. Successfully our code is going to work. There is no problem at all. If you want, you can see. But sir, I want to see the output. If you want to see the output, you have to implement the program in any one order we have to print. Okay. So let us take, I will implement level order, sir. Okay. Or I will implement in order. Okay. So print in order like this. I am taking a function. Sir, 1 second, please wait. Yeah, so try to print this in order style. So first I'm going to call this in order where I'm going to call self dot. So print in order. So utility function I'm going to prepare. Sir, why I am every time preparing utility function in the sense? So compulsory you have to pass root node, sir. Then only we can able to print, right? That's why I'm creating utility function. In that utility function, so print underscore in order. So utility function, which will take first parameter as a self. Next parameter is what? It will take some node. Suppose if the node is not equal to none, that means if the node is existed, sir, first in order means what? We have to call this self dot print underscore in order utility function we are calling recursively by passing node dot left, because in the in order first we have to visit left node, then we have to print that node dot data followed by end is equal to space, then we have to visit right. Is this is the step or not? Already I covered this. This is the recursive process what we are going to do. Okay, first it will check is the node is existed. If the node is existed, it will check is the left node is available and it will transfer the control. And if the left node is available, it will visit left. So after completion of left visit, it will print the data and then it is going to visit right. Like this process we are going to continue. Okay, so now I want to execute this. Please don't call this a utility function. We have to call the normal function. Already we have tree. For this I am calling print in order. Sir, already we implemented. We need to get a in order output like this. Let me cross check whether we are getting the same output or not. Now you can see 4, 4 to 5, 1, 4 to 5, 1. So 637. I request everyone to please switch off your video mode. So 4 to 5, 1, 637. 4 to 5, 1, 637. Sir, is our algorithm is working properly or not? Yes. This is the way how to create binary tree by using list data structure. I mean, by using the list of nodes. Please confirm, is the concept is clear for you people?
Yes, sir.
Yes, sir.
Clear.
Yes, sir.
No doubt, right?
No, sir. Clear.
Yes, sir.
Right. Sir, now can I create binary tree by using linked list? Why can't we can create a binary tree by using linked list? Sir, how to do that? Because insertion directly into the tree is not possible. That's why we are not going to call this create function explicitly. We will call in the direct creation. Now consider I want to create a tree. I don't have any method. Sir, I want to create a tree like this. Consider the root node is nothing but 2. Its left child is nothing but 1. Its right child is nothing but 3. I want to create like this. How to do that? Sir, T dot. For every tree we have a root node or not? Yes. Now I am calling tree dot. So we have to create a node, right? We have to create a node. Sir, how we are going to call T dot node of what is the data? 2, right? With this I am going to create a node. Now let us execute. What is the output that we are getting? Do you need node? N capital I have taken, I think so. You can see we have only one node is there. I want to attach this one as a left child. How to do that? So root node is there, right? Its left child will become T dot. I am creating a new node with the content 1. And 3 will become what? This root node right child. Now tell me, if you print in order for this, what will be your expected output? Please confirm.
1, 2, 3.
1, 2, 3. If I am not wrong, we need to get output as 1, 2, 3. Now consider I am going to add one more node here, which is nothing but 4, and I am adding one more node here, 5. So for whom we are attaching this 4 and 5? Root node left. Okay, for this we are adding left and right. For this we are adding left, and for this we are adding right. So what about the left data, sir? 4. What about the right data, sir? 5. Now tell me, what is the expected in order for this?
4, 1, 5, 2, 3. 4, 1,
So
5, 2,
4,
3.
1, 5,
2,
2,
3.
3.
Yeah.
So let me cross check. 4, 1, 5, 2, 3. This is the way how to create a binary tree by using linked list, and how to create a binary tree by using a list. Sir, we can't create any method like insert, like how we have done in the stack and queue in the linked list. We don't have any method called insert. We can't implement because there is no proper format. We know every node is going to have only 2 children, but we don't know which child will comes under left and which child will comes under right. That's why we don't have any flexibility. That insertion and deletion we will see in detail in our binary search tree. So now I explained the total concept of tree, the terminologies what we are using in the tree, and how we can able to work with this pre-order, post-order like that. Any doubts, friends, up to this?
No, sir. Clear.
Everyone, please confirm clear.
Yes, sir.
Right. So tomorrow we will continue this. Please don't leave the meeting. So tomorrow we are going to see these orders. All these orders I am going to explain like in order. Okay. So pre-order printing and post-order printing, and even we have level order is also there. How to print the content in the level order direction. Then how to count. So count how many nodes are there. Okay. Next, and after that, how to calculate the sum of nodes present in the tree. Next, how to calculate the height of the tree. Okay, how to calculate the height of the tree, how to implement the search operations. Okay, next and after that, how to find a max element in the binary tree, how to find a minimum element in the binary tree. Next and after that, we are going to check whether two binary trees are equal or not. How we can able to perform copy of tree, how you can able to do that. Next and after that, number of leaf nodes, how many leaf nodes are there, how to find out. Then I want to print all paths from root to leaf node. I want to print all the paths. These operations we are going to see on binary trees. Then we will see binary search tree. Sir, whatever operations that we are going to cover on tree, you can do these operations on binary search tree also. There I want to concentrate on this. Maybe except search operations, remaining things will become very simple. Okay, and tomorrow we have class from 7 p.m. to 9:30. 7 p.m. to 9:30 p.m. So you have to use the same link to join, sir. Okay, you have to use the same link to join. So first we will see the programs on this for first 30 minutes. Later we will go with binary search tree. Okay, right. I'm going to upload these running notes now itself. After completion of the class, you can download. Okay. Thank you, sir. Good night.
Yes, sir.
Good
Sir,
night.
please upload no.
Yeah,
we can
yeah, yeah,
practice.
sure. Yeah, yeah.
Yes.
Thank you. Good night.
Good night. Sir.